So this is a project joint with Pedro Freitas, and just to go back a little bit, Pedro invited me to visit him in Lisbon probably 3 years ago now. I think it was 2017. And this is the kind of thing, of course, that at least those of us in North America can't really do anymore. But it was crucial for initiating this project and bringing it to fruition over a period of a few years. And so I do hope very much that we can get back to that at some point in the future. In the chat window, you'll see the archive link for this preprint. And you're very welcome to download that and sort of read along as we go. And I know I sent the slides also to Alexander, so he can distribute those or put them on the web page afterwards. So we're trying to maximize the third Neumann eigenvalue in Euclidean and hyperbolic space. So the Euclidean case is a theorem of Bucur and Henrot from last year. And then the hyperbolic case is what's new, but we're going to get to the hyperbolic case by giving a somewhat different approach to the Euclidean proof as well, which will then enable us to extend to the hyperbolic situation. So I just had to figure out how to move forward. Here we go. Good. So the goal, to maximize low Neumann eigenvalues under a volume constraint. So throughout the talk, we're going to be constraining the volume of the set, and whether the maximizer is one ball or two balls. In every case, the competing sets all have the same volume. And Lipschitz, just so that the spectrum is discrete and we can use the variational principle, the boundary regularity otherwise does not come into it for us. So we have this discrete sequence of Neumann eigenvalues. The first eigenvalue, mu1, is 0. Now I know that this is a spectral geometry seminar, and many geometers would prefer to start with mu0 equals 0. But there are two reasons, and I've not been consistent myself over the years, but there are two reasons why here I think it's important to start with mu1. First of all, if you were thinking of extending to a family of Robin problems, and we've had some talks in this series on Robin problems, you should think of the first eigenvalue as simply being the first eigenvalue. The fact that it happens to equal 0 in the Neumann case is, one might say, an accident. The other reason is that since we'll be comparing with two-ball situations, two disjoint balls, our domain being a disjoint union, means that not only the first but also the second eigenvalue is going to be 0 when we're in the two-ball situation. So we're not assuming that this open set is connected, we're just assuming it's open, has Lipschitz boundary, so it might have one or more, finitely many, but it might have more than one 0 eigenvalue, depending on the number of components. So the intuition is that a long thin set behaves like a one-dimensional string. So we're thinking about maximizing or minimizing, and it's easy to see then that the minimization problem is not going to be interesting, because you can take a very long thin domain, behave like a long one-dimensional string, so its Neumann eigenvalues can be very low. Correspondingly, going the other direction, a concentrated set in some ways should give Neumann eigenvalues that are big, or at least we hope as big as they can be. Now, it's interesting to contrast that with a Dirichlet situation where, again, the lowest Dirichlet eigenvalue is minimal for a ball. The next Dirichlet eigenvalue is minimal for a union of two disjoint balls of equal volume. And the kind of theorems we're looking at here are going to say that, well, mu2, the second Neumann, is maximal for a ball. Mu3, the third Neumann, is maximal for a disjoint union of two balls. But it's not actually really the same phenomenon exactly. It's related, but not exactly the same. It's sort of like reverse sides of a coin. In the Dirichlet case, in order to minimize the eigenvalue, you don't want any short you don't want any short distances across the domain, because if you have a short distance going across a domain, that's going to force the Dirichlet eigenvalue to be very high. So a short wavelength, high frequency. But the reason you don't want a long thin domain for Neumann is you don't want any long distances along the domain, because that would allow you then to have Neumann eigenvalue oscillating in the long direction. So it's sort of two aspects of the same thing, but two slightly different reasons why in both cases we end up with balls and two-ball situations for these low eigenvalues. Okay, to reiterate, we're going to be looking at second eigenvalues and third eigenvalues. If we write something like mu2 of omega less than or equal to mu2 of b, that means that omega and b are implicitly assumed to have the same volume. If we write mu3 of omega less than or equal to mu3 of b disjoint union b, that means that again, the two sides, the domains on the sets on the two sides are assumed to have the same volume. So the ball does not have the same volume as omega in that second case. The ball only has half the volume of omega in that second case. And you know you're getting old actually when you start using terminology that was not around, or at least not commonly used when you're in graduate school. So I don't recall the square union symbol for disjoint union when I was in graduate school, but all of the students now seem to know it. Okay, so that's what we're looking for, maximizing second and third Neumann eigenvalues under a volume constraint. So some of the history here, and I apologize if anybody feels they're being treated unfairly here, but I felt the diagram was already complicated enough. So I tried to summarize what's happening in these three situations. And the middle actually is where things started, with simply connected domains in R2. And this was Szego in 1954, when he proved that the second eigenvalue for simply connected domains in the plane is maximal for the disk. And he was using conformal mapping techniques there, introducing the trial function to the disk, carrying them across to omega by the conformal mapping, and so on. Then Weinberger took that idea and extended to arbitrary domains in n dimensions, again for the second eigenvalue, maximal for a ball now. And it's this line of thought over here on the left side, which really we're primarily following today, to get down to this third eigenvalue result of Bucur and Henrot, and then the somewhat different proof that we have, leading on then down to the hyperbolic case. But ideas are coming in also from the other side of the diagram. Over here on the other side, metrics on the sphere. So Hersch in 1970 took those ideas of Szego in a different direction and interpreted them as telling something about metrics on the sphere. Because Szego's result, although it was formulated for simply connected planar domains, what he was really doing actually was using the conformal map to push the Euclidean metric on the domain over to the disk. And then he was working with metrics on the disk. He didn't exactly phrase it that way, but he would have understood it in those terms, I'm sure. So what Hersch did was he applied these ideas now to metrics on the sphere, which you can think of, since we're talking the two-dimensional sphere, think of in terms of just a conformal factor or a weight function on the sphere. So you think of a weighted sphere, different mass density, different points, vibrating, oscillating away. Now you need something like the conformal maps then to push the mass around in order to get your center of mass condition. So for those of you who've read any of these proofs, you know there's always a center of mass condition that has to be satisfied, which is giving you orthogonality of your trial functions to the constant state being the Neumann ground state. So Hersch there was using the Möbius transformations of the three-dimensional solid ball, which extend to the sphere, the boundary sphere, and push the mass around in a conformal way on the boundary sphere. So, right, so that's sort of our top row. The second row, let's see, so in the second row, the first result here is by Nadirashvili for the sphere, looking now at the third eigenvalue and showing that the third eigenvalue is maximal for essentially two disjoint round spheres, which you can obtain in the limit by imagining pinching off a sphere into two spheres and seeing what the metrics do. So this idea of pinching off then showed up in Girouard, Nadirashvili and Polterovich, 2009, back in the planar situation, so sort of coming around like a commutative diagram, back to the planar case, showing that the third eigenvalue there is maximal for the disjoint union of two disks. And actually I should have really drawn that sort of being two touching disks. So again, you have your simply connected domain, and imagine pinching it off so that it approaches two disjoint disks. Okay, so what were some of the ideas here? The idea that Nadirashvili introduced was an idea of folding. He phrased it in terms of folding the metric, or folding the mass density associated with the metric across a spherical cap boundary, spherical cap on the sphere, which Girouard, Nadirashvili and Polterovich transformed into reflecting across a hyperbolic cap boundary in the disk. So we now got this idea of folding. So back over to the left side in the Euclidean case in Bucur and Henrot's proof, and we'll show some pictures more precisely of this in a couple of minutes. This folding idea shows up in terms of having a hyperplane and having trial functions that are even with respect to the hyperplane. Okay, where are we now? Ah, yes, right. So then they had center of mass conditions that they're satisfied by a two-step homotopy argument with a particular vector field, which we're going to do somewhat differently today. So that different idea for the homotopy comes from back again on the right side with a sphere, where Petrides in 2014 introduced a new idea in his work that was not only for S2 but also for getting non-sharp results on higher dimensional spheres. Introduced a beautiful reflection symmetry homotopy idea for computing the degree of a map from a sphere to itself that satisfies a certain reflection symmetry property. And so we're taking that idea and using it in a slightly different way, in the same sort of spirit of things, but in a different way to complete our homotopy argument here back in Euclidean space. So once one has all of that sort of pulled together, then you can jump down to the hyperbolic case because the geometric facts that we need in hyperbolic space are all analogs in some sense of things that are happening in Euclidean space. So you need things like translations, you need hyperplanes, you need balls in order to make the argument work. Okay. Yes, so let's move on now to the mathematics. And I do encourage you, by the way, to ask questions throughout. I might see notifications, but I think Jean is monitoring the chat window. So if you put something through by chat also,
I am indeed monitoring the chat.
So yeah, if you don't want to speak up, which you're welcome to do, just put something through on chat and Jean will let me know. Okay, so what was this theorem of Doreen Bucur and Antoine Henrot? It said that the third Neumann eigenvalue of a Euclidean domain omega, Euclidean open set omega, is maximized when the domain is a disjoint union of two balls, where each ball has 1/2 of the volume. So we're going to give a proof that follows their outline, but with certain differences in key steps. So we're doing the Euclidean case first to establish a framework that can then be extended to the hyperbolic case. And so the key point then is to try to find a proof that does not rely upon anything that's sort of genuinely Euclidean, but only upon geometric constructions that can be translated to another, to the hyperbolic situation. So the trial functions in some sense go all the way back to Szego and Weinberger with sort of extensions through Girouard, Nadirashvili and Polterovich. And we're going to satisfy the orthogonality conditions. In this game, the whole business is to get orthogonality to the first two eigenfunctions. Once you have that orthogonality, then you can invoke the Weinberger machinery. So the interesting part is getting the orthogonality so that your trial functions are valid trial functions. So we'll write F1 for the Neumann ground state, which of course is just constant. And we'll write F2 for the first excited state, the second eigenfunction on the domain omega. So these two functions live on omega. Our other functions, our trial functions, are going to live on all of space. But the eigenfunctions, of course, are just on omega. Usual Rayleigh quotient and the variational characterization of the third eigenvalue. Okay, so how do we find trial functions satisfying these orthogonality conditions, these orthogonality constraints? So the motivation, going all the way back, is to construct a family of trial functions that exists not only on omega, but also on all of Rn. The reason being that you don't know where the domain is. Now, this is somewhat different from Szego's original paper in simply connected domains, because Szego pulled across with a conformal mapping the eigenfunctions on the disk to the trial functions on the domain omega. So his trial functions only existed on the domain omega. They did not exist on all of Rn or R2. So I think one of Weinberger's key insights is that to handle the general domain case, you should not try to construct a trial function that exists only on the domain omega. You should construct something that exists on all of Rn, and then adjust, or rather construct a family of such things, and then choose trial functions from that family that are well adapted to where the domain omega happens to be. In other words, choose the ones that satisfy the right orthogonality conditions. Now, we're guided in terms of what these trial functions should be by the fact that if our domain is a disjoint union of two balls, then we have no choice really as to what the trial functions have to be on those balls. The trial functions will have to be eigenfunctions on those balls. So a third eigenfunction for the union of balls. So once you have that in your mind, you realize, well, your family of trial functions should be based upon having two balls, build the correct eigenfunctions on those two balls, and then extend somehow to the rest of space. So start with the two balls and then extend somehow. So constructing trial functions, and on this page we'll just do 2 dimensions for simplicity. What's the spectrum of the disjoint union? Well, of course, you've got 2 disjoint components, so you have 2 zero eigenvalues, and then the next eigenvalue occurs twice, and so on. Actually, 4 times because it has multiplicity 2 on each individual ball. But so you've got 2 zeros, and that's the key point. You've got 2 zeros, and so the third eigenvalue is simply the second eigenvalue of one of the balls. So that tells you what the eigenfunction ought to be. Let's normalize the volume so that we can talk about unit balls here. So the eigenfunction is simply the usual Bessel function. Here we go, the Bessel function J1, scaled appropriately. And then we extend it to be constant from radius 1 onwards, and just as Weinberger did. So our 2 eigenfunctions are this radial function, the details of which won't matter to us, just the fact that it's radial and satisfies the right differential equation. And then you've got a cosine mode and a sine mode. Or, of course, you can rotate by any angle as well. But so there's 2 linearly independent eigenfunctions, and r is the distance from the center of the ball that we're building this thing on. So we're showing there the radial profile, and then we multiply by cosine theta or sine theta to get a function defined on the disk. Now what we have to do is to piece together this function on one ball with a similar function on the other ball. So we've got several things to think about. So each one of these, the cosine theta or the sine theta mode, has this distinctive nodal pattern. For the cosine, we've got left and right halves of the disk having different signs, plus on one side, minus on the other. And then the sine function is the top and bottom. We've got to think about the fact that we could potentially have linear combinations of such things. And right, and then in higher dimensions, it's not exactly a Bessel function, it's a Bessel function divided by some suitable power of r. So what we want to do is piece these things together on the 2 balls so that we get something that is a valid trial function. So in particular, wherever these 2 things match up, they'll have to agree in value. So let's now look at the picture. This is the kind of picture we're dealing with then. So, and to stress, I mean, these ideas, this reflection idea goes back in some sense to Nadirashvili with the sphere, although of course the geometry is a bit different there, to Girouard, Nadirashvili, Polterovich in the disk, where that hyperplane H would be a geodesic, and then Bucur and Henrot had this family of functions as well. So let's consider 2 balls. The locations are arbitrary. You know, the radius of the ball is fixed by a volume constraint, but the locations of the balls are arbitrary. And we've shown them being disjoint, but in principle, if the centers of the balls are close enough, the balls might actually be overlapping. So one has to have a construction that works for that case as well. So given the 2 balls, you can put a hyperplane that's equidistant from the center points. So we've got a hyperplane H. And we can construct 2 modes, the cosine theta and sine theta mode. And here we're showing in the bottom ball, the bottom left ball, we're showing the cosine mode. So plus on the right side, minus on the left side. Now, then we can extend, because we've extended our G of R. Remember, G of R comes up, levels off, slope 0 due to the Neumann boundary condition, and then we extend it to be a constant. Having extended it to be a constant, that's the green dashed lines outside the ball there. So inside the ball, the function G of R is radially increasing along each ray, and then you're multiplying by the sine or the cosine of theta. And then once you reach the boundary of the ball, you just continue that value outward along the ray until you hit the hyperplane H, if you're heading in the direction where you will hit it. When you hit it, then you stop and you reflect across in an even fashion following the ray that leads you back to the center of the other ball. So by this method, you can extend from one side of the hyperplane, extend the function evenly over to the other side of the hyperplane. And I hope that picture gives you some sense of how that extension goes. So to be clear, those are not contours, those are not level curves of the function. It's rather showing you the rays along which we extend the function from the center of one ball out to the edge of the ball, and then continuing until we hit the hyperplane and then reflect. So we need a large family of trial functions because we have a lot of orthogonality conditions. So it's a good idea to count up how many parameters we have and to see whether that's, even in principle, sufficient to meet the number of conditions that we have. So in 2 dimensions here, how many trial functions do we have? Well, we're starting with a cosine theta mode and a sine theta mode on one of the disks. So that gives us 2 trial functions. Each one then extends, reflect across the hyperplane. So we've got 2 trial functions. How many orthogonality can, sorry, what am I saying there? No, I think what I meant there is, yeah, sorry, I think what I meant to say there, instead of how many trial functions, how many eigenfunctions are we going to have orthogonality to, and that's 2 of them. Anyway, so how many orthogonality conditions? Well, we've got, we have to have the trial functions each orthogonal to F1 and F2. So that's going to be 4, well, okay, so I suppose for each choice of disks, we have 2 trial functions, put it that way, the cosine theta mode and the sine theta mode. How many orthogonality conditions? Well, we have to have each trial function orthogonal to the first and second eigenfunctions. So 2 times 2 is 4. And how many parameters do we have? Well, fortunately, also 4, because there's the center of each ball. Each center point has 2 real coordinates, so 4 coordinates in total. So from that perspective, it seems promising. And this sort of parameter counting, of course, goes back also to these earlier authors. Now, in n dimensions, we've got n trial functions because cosine theta and sine theta generalize in n dimensions to the n spherical harmonics of degree 1. So there's n of those. 2 n orthogonality conditions because we have the 2 eigenfunctions that we need to have orthogonal to each of the n trial functions, so 2 n orthogonality conditions. And again, we have 2 n parameters because each ball center has n coordinates, 2 balls, 2 n coordinates. So the parameter counting works out, but of course it's a nonlinear problem in many ways, and so it's not clear that just because you have the right number of parameters, you're going to be able to solve the problem. So you've got to find some insightful way of breaking it down. So this is where the proof that that Pedro Freitas and I present diverges from what Bucur and Henrot did in terms of how we satisfy these orthogonality conditions. Okay, so we're going to parameterize differently now, and we're going to parameterize in a way that follows what Girouard, Nadirashvili and Polterovich did, rather than using the centers of the balls as the parameters, which is what Bucur and Henrot did. We're going to parameterize using the center of one of the balls, so that gives us n parameters. And for the other, we'll use the hyperplane. So go back to this picture here. So the hyperplane is determined again by n parameters because you need a direction, that's p, a unit vector, unit normal. So that's a vector on the unit sphere, so that's n minus 1 parameters. And then you need to say, well, what's the height of the hyperplane? In other words, how far have you translated the hyperplane in that normal direction? So that's 1 more parameter. So we still have 2 n parameters, c, the center, p, the unit vector, and t, the height of the hyperplane. Now, okay, how are we going to use this? For compactness of notation, rather than listing out each of the n different trial functions, so in 2 dimensions, it's just cosine and sine modes. In higher dimensions, we use x over r, where x is the vector away from the center, if you like, and r is the length of it. So this is a vector. So every time you see v, think vector. This is our vector of trial functions, vector field of trial functions. And still, we have our radial profile of the Neumann mode of the ball. So g of r is our radial profile of the Neumann mode for the ball. And then g is extended to be constant outside the ball. Okay, so what are we doing then with this construction on the previous page? You see we're centering around this point C here, and then we're extending, and then we want to reflect. And a compact way of writing that operation of extending and reflecting is the centering is by the minus c. So I've centered our vector field at that point c. And then FH is a fold map that enforces evenness across the hyperplane. We need evenness across the hyperplane so that, for instance, our trial function does not jump. The trial function is allowed to have sort of corner points or a ridge line along the hyperplane, but in order to be in the Sobolev space, it should not, for instance, have any jumps. So we enforce that evenness with this fold map, which fixes one half space, the half space that contains the point C, and folds the other one onto it. So if we go back to the previous page and look at the picture, the fold map is leaving our lower left side of the hyperplane alone, and on the upper right side of the hyperplane, it's just folding it over, reflecting it over onto the lower side of the hyperplane. So this gives us a trial function, or vector of trial functions, that is even with respect to the hyperplane, even with respect to reflection. Okay, so we should think of C as our origin, if you like, for the trial functions. And again, the components of that vector field, the components are giving us the individual trial functions. So first we need orthogonality to the constant, and Weinberger, Szego and Weinberger showed how to do this with the Brouwer fixed point theorem, that you write down your integral. So this left side is integrating our trial function against the constant function 1. We want that integral to be 0. So regard the left side as a vector field. For each hyperplane H, we want to choose this translation. We want to choose a translation in order to center the trial functions and make them all orthogonal to the constant. So you think of the left side as a function of that C vector, and then you can apply Brouwer fixed point because you know how this vector field behaves when C is very far away from the origin. But we need more, actually, for the rest of the argument. We need not only that there exists a center of mass point, so sort of centering the, so that what the fold map does is it folds part of the mass of the domain, part of the volume, over onto the other part, and then think of it as being like traditional center of mass. Once you've folded the mass density over, then you want to find where the center of mass is and center your eigenfunctions on that point. But we need more than just existence of the center of mass, because we also have to deal with these other parameters in the problem. So we're going to need some sort of continuous dependence. And this was done in the disk case, by GNP in 2009. They showed that the center of mass depends continuously on the parameters of the hyperplane. So in other words, as you might imagine for each choice of hyperplane, there's some center of mass point, which depends on the domain omega, right? The domain omega is not shown. But if we had the domain omega on there, we would then center that one ball with a center point C appropriately to get the center of mass point for omega. But then you start moving the hyperplane around and you want to know where the center of mass point goes. Well, we want to know it changes continuously as we move the hyperplane around. So that's this continuous dependence result over here, that the center of mass depends continuously on the parameters of the hyperplane. They proved it with some calculations in the disk that gave them certain sort of monotonicity properties that enable them to get the continuity and the uniqueness and the continuous dependence of the center of mass point. There's a more recent proof this year using energy methods. Essentially, you want to think of, you use the analog of the moment of inertia. So for classical center of mass, the center of mass is the point that minimizes the moment of inertia, when moment of inertia is taken with respect to that point. So you want to use the analogous idea for some well-constructed energy related to this vector field here. Okay, once you've got the continuous dependence of the center of mass, then you've got to still satisfy orthogonality to the second eigenfunction. And here, it turns out there's a helpful property. And this aspect is new, actually. It sort of seemed a small step, but it helped simplify the argument considerably. In the GNP paper from 2009, they had a certain sort of flip-flop property where they considered not only hyperplanes that are very far from the origin in one direction, but also hyperplanes that are very far from the origin in the other direction. And when you go in that other direction, in the disk situation, it was quite subtle to understand the behavior of the center of mass point and related quantities. what Pedro and I realized actually, though, is that you can get away with only using t greater than or equal to 0. In other words, only using hyperplanes that lie on one side of the origin. You don't have to consider hyperplanes that lie on both sides of the origin. In the sense that once you fix your direction p, it's enough to consider hyperplanes with t greater than or equal to 0. So going in that direction, starting from the origin, and then going off only in the direction p. You don't have to go in the other direction. And the reason you can get away with that is that when the hyperplane goes through the origin, it satisfies a certain symmetry property. And so, the picture is supposed to indicate here that when the hyperplane goes through the origin, you see if you reverse the direction of the hyperplane, reverse the p, and instead consider negative p, then what you've done is you've interchanged the two half spaces. Right? So if you change the p to negative p, that simply flips the role of the two half spaces. And then you chase through the definitions and you realize this tells you that the center of mass point gets reflected through that hyperplane. So Rp is reflection in that hyperplane. So with that, we're going to be then able to bring in this result of Petrides that I mentioned earlier. Okay, so reflection symmetry of the center of mass point, which I hope is at least intuitively reasonable, even if you haven't gone through the formulas. So then we want to use that to get orthogonality to the second eigenfunction. And so here, what are we trying to do? So we want this integral here. We want to integrate our vector of trial functions against the second eigenfunction, F2. So let's call that W, just because W comes after V in the alphabet. So for each hyperplane depending on the direction P and the height T, we cook up our trial functions and we integrate against the second eigenfunction. And we want to get 0. So we start by saying, well, when do we know something about this thing? Well, we do know something when T is very large, when T is very large positive. So imagine moving a hyperplane very far off away from the origin. And in that case, the domain omega lies all on the lower side of the hyperplane. And in that case, remember, that's the side of the hyperplane that's not affected by the fold map. The fold map is just the identity there. So in that case, we claim that the fold map is just the identity. And coming back to here, where we define the center of mass condition, if the fold map here is just the identity, then we can see we choose the same center of mass point no matter what H is. So if H is very far away from the origin, does not matter which direction it's in, so long as it's very far away from the origin so that omega is contained in the lower hyperplane, then the center of mass point is going to be the same for all of them. So that means here that CH is the same for all hyperplanes that are far from the origin. In other words, we're getting a constant, right? Because if CH is the same, then we're going to get the same thing here in our integral. So this vector field W that we want to show equals 0, at least we know it's constant when the hyperplane is very far from the origin. And that starts you thinking about degree theory. And these sort of ideas go back, of course, to Szego as well, who was thinking in terms of degrees. So now we've got something essentially of degree 0. We've got a constant vector field. So how can we get a contradiction and hence find that W has to equal 0 somewhere? Well, we'd like to find something that has non-zero degree that's homotopic to this thing that has 0 degree. And that would then be a contradiction. So orthogonality to the second eigenfunction then. Just a reminder of what our vector field is, giving us the integral of our trial functions against the second eigenfunction, and we want them to be 0. So the key point is that reflection symmetry thing when the hyperplane passes through the origin. So again, if you chase through the definitions, the reflection symmetry shows up in this vector field here, again as being reflection symmetry of this W vector field, the integral of the trial function against the second eigenfunction. And so the elementary but useful fact that lies behind this is simply that our vector of trial functions, the V here, commutes with reflection in that hyperplane through the origin. There's nothing deep there. The vector field has this x over r in it, like the cosine theta sine theta thing, the x over r, and that commutes with the reflection. Oh, sorry, when I say commute, I mean you can pull it out. If you apply the reflection to that, you can pull it out through the vector field. Okay, so we've got reflection symmetry, and then we come to the result of Petrides, reflection symmetry degree theorem. That's what we're calling it, not what he called it, but he was using it in a similar context on the sphere, although not exactly the same. There were sort of two-dimensional spaces of trial functions and so on involved there. So what we realized is we could adapt it to our situation to use it here for the t=0 case, when the hyperplanes go through the origin. And so it's a beautiful theorem. It says, it's sort of a little like the Borsuk-Ulam theorem that says if you have an odd, if I'm remembering this correctly, you have an odd map from a sphere to a sphere, then it's going to have non-zero degree. Well, here it's not oddness, but it's something to do with the antipodal point still. It's saying that if your map from the sphere to the sphere has the property that at the antipodal point, the value of it is the reflection of the value at the original point. So not the negative of the value at the original point, but the reflection. And so there are these arrows here are supposed to indicate what's going on. So one simple case would be here where at that point, the vector field, the map, think of these vectors as giving a point on the sphere. These are all supposed to be unit vectors. So the image point, excuse me, is in the same direction. Then over here, the image point at this opposite point would be in the opposite direction, which is what you get by reflecting through the hyperplane perpendicular to the point that you're at. But over here, a little bit more interesting, here we've got P, and then we're indicating 5P is this unit vector pointing in that direction. And over here at negative P, we have to reflect that point. So we've reflected, so here we've got the hyperplane through the origin that's perpendicular to the point where we're sitting at. So we've reflected like that. Or if you like, look at the tangent plane. Another way to say it would be look at the tangent plane at that point and reflect across that tangent plane, and that gives you the vector that you need over here. Now in one dimension, sorry, in the one-dimensional sphere, the circle here, it's not too hard to convince yourself the degree has to be non-zero. There's a winding number argument you can do in the plane. But it really becomes non-trivial already in 2 dimensions. And so it's really quite an insight to see that this degree is going to be non-zero. And in fact, Petrides proved more than non-zero. He identified that in odd dimensional spheres, this degree is going to be 1, and in even dimensional spheres, the degree is going to be an odd number. So always non-zero, and that's what we need. So 2 proofs now available. There's one, the original one, using what you might call a local surgery approach, sort of zooming in on special points of the map and then flipping things. And then we have a different approach, which is more of a global approach. The idea is essentially is to look at, so here 5P is pointing outwards at all the points we're seeing, but 5P could be pointing inwards at some points. And what you want to do is wherever 5P is pointing inward, you want to reflect it and pop it so that it points outward. And you can do that, of course, because the interface between the 2 regions would be where 5P is tangential, and at those points you're not affecting the map at all. So this is a continuous surgery that we're doing. Anyway, okay, we won't go into the details of that proof, but we will use the result. So how do we use the result? Well, if W is never 0, which is bad for us, then in some sense it's good because we can normalize, and we get a phi. Phi here depends upon P and upon T, so now we can use a homotopy argument. And we know what happens when T is very large. When T is very large, this vector field is constant when hyperplanes are far from the origin. And so we get degree 0. But Petrides implies, using reflection symmetry, that when T = 0, when the hyperplane goes through the origin, the degree is non-zero. Okay. So degrees are homotopy invariant. So this cannot be right, which means that W must vanish somewhere. So there must be some hyperplane you can choose for which the vector field vanishes. And that means you've got orthogonality not only to the first eigenfunction, which is what you achieve by choosing the center of mass, but you've also got orthogonality of the second eigenfunction by choosing this correct hyperplane. Remember, the choice of the hyperplane also then determines the second ball. So we're choosing the first ball with the center of mass, find the hyperplane by the second orthogonality condition, that determines the second ball by reflection. And just to reiterate, Bucur and Henrot's homotopy proof was really very different. It had two n parameters. They were, whereas we'd reduced here to an n parameter problem, they were still working with the two n parameters, and they had a two-step explicit homotopy argument to reduce to a certain vector field whose index they could then compute. Okay, once you get to this point, it's all downhill. I'm a cyclist, so I like it when I get to the all downhill part. Here we can follow Weinberger's method, monotonicity of g squared in the denominator of your trial functions, of your Rayleigh equation, and in the numerator, whatever it is you get from plugging in the trial functions and averaging over all of them. The reason that we need so many trial functions, by the way, is that we essentially want to use that cosine squared plus sine squared equals 1 in 2 dimensions, or the analogous thing in higher dimensions. Otherwise, we would not know how to estimate the things that we end up with. But by averaging over all those different trial functions, we get to average out all the angular parts, and we're left only with the radial parts. Once we have just the radial part, g, then we can use monotonicity properties and sort of mass transplantation, move things from outside the ball into the ball. Now, it's true that here we have two balls, but it turns out that's really not a problem because of the folding and the symmetry and so on. The argument, Weinberger's argument, really carries across just the same. So to summarize the proof, I know there's quite a lot to take in, but the steps are build the trial functions from centering on one ball and reflecting across a hyperplane. The trial functions depend on two n parameters, the center of the ball and then the hyperplane itself, the location of the hyperplane. So use the center of the ball to satisfy orthogonality to the constant for all of your trial functions, and you use the location of the hyperplane to satisfy orthogonality to the second eigenfunction. And that's where the homotopy ideas and the Petrides theorem come in. Right, so I did promise something about hyperbolic space, and so I'll at least state what the operator is and what the theorem is, but we won't do the calculations. So we're now dealing with a hyperbolic space, which I like to think of as the hyperbolic ball. And so we're going to work out the Laplacian in the ball model, but that's just a model of hyperbolic space. There are other models as well. We'll write eta being the Greek letter for h, hyperbolic. So eta for the eigenvalues of the Neumann Laplacian. And the claim is that eta 3, whatever this Neumann hyperbolic Laplacian is, that the third eigenvalue is less than or equal to the third eigenvalue of the disjoint union of two hyperbolic balls, each of which has half the hyperbolic volume of omega. So what is the Laplacian for the hyperbolic metric? You apply the formulas from Riemannian geometry, the metric, the hyperbolic metric. So I know not everybody is, well, I suppose this is a spectral geometry seminar, so maybe everybody is familiar with the hyperbolic metric. But in the ball model, you just take 1 over, down here, take this 1 over x squared, 1 minus x squared, put it in the denominator and square it, and then multiply that by the Euclidean metric. And that gives you your hyperbolic metric on the ball. So in particular, then, the distance from the origin of the ball to the boundary of the unit ball is infinite in the hyperbolic metric. So what do we get for the Laplacian? Well, you look at the Laplace-Beltrami operator for this metric, and this formula here is what drops out. So it's a weighted Laplacian, a weighted Euclidean Laplacian, where we're using the radial weights. Many people prefer to use more intrinsic coordinates, where you would use the hyperbolic distance from the origin instead of the Euclidean distance from the origin. So here we've written it in terms of the Euclidean distance, modulus of x, from the origin, which we found works out quite conveniently. But other authors who've worked on the hyperbolic Laplacian tend to use the intrinsic distance. And then for knowing what to do with the argument, we really need the Rayleigh quotient. So here's our Rayleigh quotient Q. And you see it's weighted in two ways. The gradient term here is weighted. So that's the Euclidean gradient. I want to stress that's the Euclidean gradient. So because we're not using the hyperbolic gradient, we have to throw in this weight factor, which would convert the Euclidean to the hyperbolic gradient. And then we have the mass density, or the hyperbolic volume element, given here in terms of this weight function. So all very explicit. And in terms of the estimates we need, we've got explicit radial functions to work with. So with that hyperbolic metric then, do we have the right geometric ingredients? So here's a picture in 2 dimensions, which is something that many students will see when taking a first complex analysis course. And here's a geodesic, which should be thought of as a hyperplane in the hyperbolic ball. Here are 2 balls of the same volume, the same hyperbolic volume. The one that's closer to the boundary looks smaller in the Euclidean sense, but of course it has the same hyperbolic volume as this other one here. So we've got balls, we've got hyperplanes. In the higher dimensional case, this would be a portion of a sphere rather than a portion of a circle. And we've got hyperbolic reflection. So for the reflection, we won't write down the formula, but the idea is simply push this hyperplane over until it goes through the origin, at which point the hyperplane is a Euclidean hyperplane. And then you can do a Euclidean reflection across, and then you push things back again. So how do you push things across? You do it with the hyperbolic isometries. Hyperbolic isometries are Möbius transformations in the disk. So we should think of it as being just like Euclidean reflection across a hyperplane. So we've got the geometric elements. We need hyperplanes in order to construct our trial functions, and here we have hyperplanes. Parameterized again by direction and by height, t, which tells you how far the hyperplane is from the origin in the disk. And the reflection is a hyperbolic isometry. That's important also. See, all these things that we don't think about in Euclidean space become important in some other geometric context. So the fact that also that the translation is an isometry. In Euclidean space, here we have the hyperbolic translations, which are these Möbius transformations in 2 dimensions, and there are similar but more complicated Möbius formulas in higher dimensions. I mean, this is all well-known stuff. So we have an analog of translations. So what does this map TC do? TC, if you think of a hyperbolic ball with hyperbolic center at the point C, then you apply the TC, this translation map, to it. That will subtract off the C and move the ball back so that it's centered at the origin. So the numerator here looks like the Euclidean part, and then the denominator is what's needed to make it work out to be a hyperbolic isometry. But the idea is still the same, that it would take the center of a ball at C, move it back to the origin. And then, of course, we're going to need the hyperbolic center of mass to get orthogonality of the constant. And existence had been done previously using Brouwer fixed point type ideas by some of the authors mentioned earlier, Chauvel and Ashbach, Ben-Gurion, and Shu, and Bandler earlier in the simply connected case. But we also need continuous dependence and uniqueness, and that's in another paper this year, to get well-posedness of this, excuse me, of this hyperbolic center of mass. The hyperbolic center of mass means you take your mass density on the domain omega, and you want to apply a suitable map T sub C, C being the center of mass point, so that when you apply the T sub C, you get a region whose Euclidean center of mass is at the origin, with respect to this weight function G, the eigenfunction, the radial part of the eigenfunction. So it's a similar idea to what you do in Euclidean space, but you have to use the hyperbolic translations. Okay, so that's a well-posedness result we can call upon, which was developed, in fact, in order to carry out this project. Okay, so we're almost at the end, so I want to have a few minutes here to suggest some future directions, and then for questions. You might be thinking, well, maybe the 4th eigenvalue is 3 balls, but it's not. So numerics by Antunes and Freitasch back in 2012 showed us what the optimizers seem to look like there. And this has been confirmed by other authors. I think Antunes and O'Day have a survey paper as well. So we're fairly confident it's not 3 balls. It looks sort of like 3 balls that have been squashed together, but it's not 3 disjoint balls. Another very interesting and relatively, well, both old and new approach is to maximize averages of Neumann eigenvalues. So averaging makes things better. So what if we take some sort of average of the eigenvalues? Maybe then it's maximal for the disk instead of for 2 disks. And this idea goes back to, well, Szego's approach, but Weinberger, I think, made the observation that the harmonic mean, that is where you take the average of the reciprocals and then take the reciprocal. So this is your harmonic mean. harmonic mean of those mu2 and mu3 is maximal for the disk. So Szego proved mu2 is maximal for the disk, and Weinberger observed that the same argument actually gives that the harmonic mean of the first, of mu2 and mu3 is maximal also. And I'm not quite sure what the current status of this is for arbitrary domains. I'm pretty sure it's certainly not been proved for arbitrary domains. Whether anybody ever found a counterexample, I'm not quite sure. But there's something that's very close. Maybe somebody on the chat can chime in there. But there's something very close, a paper by Wang and Xia from 2018 in n dimensions. Not, all right, so in n dimensions, you'd like to go up to the n plus first eigenvalue, just like in 2 dimensions, you go up to the third eigenvalue. Wang and Xia almost got there, and maybe in fact this is the best that can be done, I don't know. They averaged the n minus 1 eigenvalues from mu2 up to mu n. So in 3 dimensions, that would be mu2 and mu3. But in 2 dimensions, it would just be mu2. Taking the harmonic mean of those eigenvalues, showing that's maximal for the ball. So I think that's a really interesting and beautiful result. And in 3 dimensions, you can contrast that with the Bucur and Henrot results and then our result in hyperbolic space, where this would be saying in 3 dimensions that the harmonic mean of mu2 and mu3 is maximal for a single ball. Whereas Bucur and Henrot is saying that mu3 by itself is maximal for 2 balls. So the averaging really changes. Even just taking the harmonic average here really changes what the maximizer is. Flips it from being a single ball for mu3 to being, that's right, from two balls for mu3 to being a single ball for the harmonic mean. And then a last question, something that my academic brother Carlo Moporgo worked on in his thesis and ended up doing stuff on the sphere instead, is looking at spectral zeta functions. So the question is still open. Does the ball, as far as I know, does the ball minimize the spectral zeta function? So that's kind of like a harmonic mean of all of the eigenvalues, or if you took the reciprocal, it would be a harmonic mean of all the eigenvalues. So you'd ask, well, is that thing, because we're not taking the reciprocal now, we're asking, is it minimal for the ball? And the interesting thing here is that in both extremes, we know the result is true. If you let s tend to infinity, the exponent in the zeta function here, if you let s tend to infinity, then the first non-zero eigenvalue here, the mu2, is going to dominate. And so you'll get back to Weinberger's theorem. And in the other direction, you can use the heat trace asymptotics and see that it's equivalent to the isoperimetric inequality as s goes to 0. So we know both endpoints are true, and in between, I don't know. So it'd be interesting to see any sort of progress really on that question or sort of related variants, I think. And that's where I shall stop. Thank you.
Thanks, Rick, for this talk. So now will be question time. Does anybody have any question for Rick? You can either unmute yourself or ask them in chat.
I have a question.
Mm-hmm.
Rick, can you go back to the slide with Petrides?
Sure. And sorry, who is speaking?
It's Misha Krapukhin.
Yes. Hi.
Hi.
Where are we? This one. Yeah.
Yeah. Right. So I have first is a question about the proof. So do you think it's possible to use the symmetry type argument to do like 2n parameter right away without going to the center of mass first? And then...
Yeah, that's an interesting idea. Right. So rather than use the uniqueness and continuous dependence of the center of mass to satisfy one set of conditions and then use this theorem to satisfy the second, can you do it all at once? I don't know. I don't know if Pedro and I tried seriously with that. I mean, sorry, I don't recall trying seriously, but I don't know if we thought about it at all. Yeah, I don't know. That's a nice question.
Yeah, but the reason I'm asking is that in the paper of Daniel Stern, we actually, for the sphere, we have basically somewhere in the paper had alternative proof for the third eigenvalue in the sphere. And there we do it without, like all parameters in one go without appealing to continuity of center of mass. And the argument is just, it's basically the same argument using this reflection degree theorem.
Good. I should follow up with you. I know we've talked a little in the past, but I don't recall exactly what you're referring to. So I'll follow up with you.
Yeah, I think I mentioned it. Yeah, I think I mentioned it in regards to your paper with Alex on on the raw band where you had the problem of continuity of the center of mass.
Yeah.
And I remarked that it's possible it can avoid it. And just a last remark is that maybe to give some perspective on this reflection symmetry degree theorem, is that if phi is smooth map, like somehow in a sense non-degenerate smooth map, then this is a particular case of Lefschetz fixed point theorem.
Oh, okay.
It's the immediate consequence of Lefschetz fixed point theorem. And basically what Petrides is doing, I don't know what, it seems like Petrides knows about it, but he doesn't say it. What his argument amounts to is just some sort of density argument to show that continuous map is always close to the non-degenerate smooth map.
Right, approximate or something, yeah.
Yeah.
Oh, that's good, yeah. So, I'm very far from knowing much about degree theory, so that's a very helpful tip. Thank you.
All right, thanks, Misha. Does anybody else have a question?
So, this is Dima Jacobson speaking. Suppose you look at some left invariant metric on a Lie group, I don't know, Heisenberg group or something, or solvable. So then things are not isotropic, but can you still ask for some sort of extremal problem for domains in that geometry? It's kind of a geometric question.
Yeah, I don't think I have anything useful to say about that. Maybe somebody in the audience does.
I don't know, I mean, maybe there is no extremum for some silly geometric considerations, but it seems like, maybe that could be a reasonable next question after, I don't know, hyperbolic, spherical, and Euclidean, right? I mean, that.
Well, it's Alexandre here. I was just going to ask a question, maybe that is in the same direction, but maybe simpler. I don't know. I don't know if there are like classes of spaces where you have families of reflections, like you have in a hyperbolic space. So maybe Dima, or if there are like classes of manifold where you have the equivalent of a family of reflections that could be used like that.
Well, I think certainly maybe you may have some things for some Lie groups, but I have to look at. I can't look specifically, but it seems like somewhat symmetrical. I don't know. There's a question. I think there may be a related question in the chat now.
Yeah, there is a question, I guess, by Hadrian Kwan about wondering if there's known results for subelliptic operators of the first and second eigenvalues or third eigenvalue for, say, rank 1 symmetric spaces.
But yes, sorry, I suppose this was in question. This was in response to Dima's question, which is it's not clear to me if there are analogous results of the sort of simpler kind that you're asking for about the Heisenberg group. Where in that setting, you maybe wouldn't look at the Laplacian, but say some subelliptic second order operator associated to this
Right.
structure.
That could be more natural for it. Yeah, I don't know, but just play around in other geometries. Of course, you can also ask like SLN mod SON. You can ask for higher rank. These are also symmetric spaces.
I think in the higher rank case, it would be interesting because they're sort of precisely along this line. You would not necessarily have sort of hyperplane reflections, or rather you would have more than one competing reflection one could consider.
Yeah, so I guess like the most interesting case could be rank. The simplest interesting case could be rank 2, right? Like SO3 mod SO3. So something like this. Yeah. Summer project.
All right. Yeah, thanks.
I have another question here. It's Alexandre. Rick, do you know or think that for the next eigenvalue, you said that three balls are not maximizing, but have you tried to construct trial functions from three balls? Even if it's not maximizing, maybe you get a nice bound that is not sharp.
Right. So the idea of getting a non-sharp bound by a trial function method. You know, I've not tried that, yeah, obviously you've got to think carefully about how you're going to match these things up. If you've got three balls and stuff coming out from each ball, how you're going to match it up in a consistent way to get a solar function valid for being a trial function. So, so I don't know. Maybe it's possible, but I don't know.
Thanks.
Are there any? Oh, there's another question in chat from Selma Yildirim, who's asking if there's a connection between minimization of Dirichlet eigenvalues and maximization of Neumann eigenvalues.
You know, at the beginning of the talk, I don't know if Selma was on at the very beginning, I gave a little bit of intuition as to maybe why sort of the two problems seem to have similar answers, but sort of it seems to be for different sides of the same coin sort of reasons. You know, for Neumann, to maximize, you don't want any long lengths along the domain, and for Dirichlet, you don't want any short ones. But it's sort of an interesting question whether there's something more precise than that. Is there any sort of way in which you can directly connect the two problems? I don't know. If there were, it would be very interesting.
Mm-hmm. One thing's for sure is that the matching part about trial function matters much less for Dirichlet eigenvalues, right? So it's easier in a sense.
Yeah, I mean, at least the methods for proving the theorems are very different. You know, lower bounds for Dirichlet, upper bounds for Neumann. Yeah.
Yeah. Are there any other questions for Rick? I had one actually. So at the end, you mentioned about something about you mentioned something about the maximizer for the fourth eigenvalue, which would not be three balls. And I know that for Dirichlet eigenvalues, there is a result by Amandine Berger saying that the disk is not a minimizer infinitely many times. So it can only be minimizer finitely many times. Do you know if there's similar results for Neumann eigenvalues where we know, and when I say the disk, I mean the disk or unions of disk, that after some point it needs to be something else than disk or unions. Do you know if there's something similar for Neumann?
I don't know that. If Pedro is on the line, maybe he knows something, or somebody else in the audience. Okay, nobody speaking up.
I guess I may ask Pedro at some point.
Yep. Sorry, just I don't have that at the tip of my tongue. So.
Oh no, it's all right. I was just wondering for further directions similar to what you have. I guess we have maybe time for another question. Oh, so there's another one from Selma again. When you say three balls squashed together, do each two pair connect at most 2 points?
If I remember the picture correctly, it's kind of like you take three balls and you sort of pack them together as closely as you can, and then it's kind of like you put cling wrap around them, so it's sort of smoothing out the places where they're coming together. So it's really I mean they're you know it's just a solid, kind of like a three-leaf clover sort of thing, but pushed together.
Oh yeah. And Hadrian, you had another question?
Yes, sorry. I wanted to ask sort of in reference to this question about the spectral zeta function. I guess, do you have some, some ideas about how you might approach this, sort of going off of maybe more Pergo's work? Because you said he had thought about this in the case of spheres. I think you would probably want to take a quotient first, right?
Yeah, I think what happened is probably my late advisor, Al Bernstein, would have known the Luttinger results about the spectral zeta function and the heat trace being maximal in the Dirichlet case for the ball, and would have asked the same question about Neumann, and probably gave that as a question to Carlo Morpurgo, who would have started working on that aspect and then realized that that seemed very difficult, but on the sphere you could at least get some local results. So I don't think there's really anything known there. I don't think there are even any local results. Local meaning sort of deform around a disk and show local stability or something like that. If you're interested, I think the place to start would be start with his papers on the sphere.
Okay. Thank you.
You're welcome.
All right. Well, I think it was a great talk, Rick, which generated a lot of questions. So thank you very much for the talk today.